Welcome to this special lesson on the A320 family limitations. I've decided to put together this particular presentation to cover all the limitations on the Airbus A320 family in one common lesson. We go through the limitations individually in the systems as we go through the A320 ground school. However, it is important that we fully understand the limitations, and therefore I put together this particular presentation to cover them all. In this 60-minute lesson on the Airbus family limitations, I will cover and outline all the limitations on the aircraft. This is to ensure a firm understanding of each limitation as we go through them, but also to summarize them all so that we don't miss any limitations during our training. This presentation can be a little bit dry as there's going to be a lot of numbers and figures running around, but I'll try to add to the limitations the specific reason why the limitations exist to make it a little bit easier to swallow. I will, in some cases, refer to the FCOM for the appropriate limitations instead of listing them on the presentation. And this is intentional because some limitations do differ based on aircraft models. I will also reference in the bottom corner, as always, the appropriate reference to the FCOM limitations chapter. Let's begin. We will start with the aircraft general, and we will start with the loading limitations on the aircraft. The load limitation is placed on the aircraft based on structural integrity of the aircraft. We have learned in mass and balance about the structural strength of an aircraft, and we've learned what happens if we exceed the maximum structural capability for the airframe, etc. We talked about design limiting load, design ultimate load, and we talked about safety factor. We've also, in our ATPL theory, covered the requirements for load limitations on specific categories of aircraft. The transport category aircraft has a maximum load limitation of 2.5 Gs, and this is where our limitation sits as well. Flight maneuvering load limitations and acceleration limits on this aircraft in clean configuration is minus 1 G to positive 2.5 Gs. In all other configurations, the maximum load limitation is 0 G to positive 2 G. The load factor protection on this aircraft in normal law and the incorporation of the fly-by-wire technology ensures that these limitations are not exceeding, providing we're normal operation. The envelope for operating the aircraft is also given in the general chapter for the FCOM limitations. Here we can see that the maximum elevation for takeoff and landing is 9,200 feet, and the minimum elevation is minus 2,000 feet. While the aircraft is capable of operating up to an altitude elevation of 14,000 feet, and we can set this manual elevation on the overhead pressurization panel. Above 9,200 feet, the aircraft requires special authorization and certification, so the normal maximum elevation for takeoff and landing is 9,200 feet. The maximum operating altitude for the aircraft is 39,800 feet. We can also see here the minimum and maximum temperature for the aircraft during takeoff and landing. On the ground, there are things we have to consider when operating. Airport operation limitations include runway slope, the altitude we just mentioned for the runway, as well as the nominal width for the runway. The runway slope is limited to plus or minus 2%. This is a mean value for the runway slope. Runway altitude is limited to 9,200 feet, we covered that, and the runway nominal width is 45 meters. The runway nominal width is used for an aircraft to do a 180-degree turn on a runway in order for the pilots to back taxi. This is crucial if you are landing or operating on a runway that does not have a taxiway at the end of that runway. We may need to back taxi in order for us to use the entire length for takeoff. Or after landing, we may have to back taxi if we miss the last exiting taxiway. This is the minimum width in which the pilots can perform that 180-degree turn to back taxi. There are also limitations placed on the aircraft based on wind. These limitations include crosswind, tailwind limitations, as well as limitations for operating the cargo doors and cabin doors. The maximum certified crosswind for the Airbus A320 family is 38 knots, gusts included. Note that the maximum certified crosswind for takeoff and landing, as I just stated, is not an airplane flight manual limitation. It is a maximum crosswind condition experienced during the aircraft certification campaign, and Airbus therefore recommends that operations should not intentionally take place in crosswinds exceeding these values, as this is outside of what the aircraft was tested on. Some aircraft may have a limitation for crosswind of 35 knots. This is, however, a limitation based on engines, not the aircraft. And this is specifically applicable to newer models of engines, so the newer versions of engines. Wind limitations also include, as I mentioned, tailwind. Maximum tailwind for takeoff and landing is 15 knots, and this is a limitation. The maximum tailwind limitation is placed on the aircraft to ensure that the airfoils, the wings, generate the appropriate amount of lift for takeoff and landing. For landing with tailwind greater than 10 knots, we should use flaps full only. Always refer to the FCOM limitations chapter for wind limitations, as they can be specific for your model of aircraft. Wind limitations are also placed on operating the doors around the aircraft. Maximum wind for operating the passenger door, that means opening and closing the passenger doors, is 65 knots. The maximum wind for operating, opening and closing the cargo, forward and aft cargo doors is 40 knots. However, this limitation can be increased to 50 knots, provided the aircraft nose is into the wind or if the cargo doors are on the leeward side. That means the side away from the wind. Forward and aft cargo doors must be closed before the wind exceeds 65 knots. While the limitations for crosswind was not an airplane flying manual limitation, it was a recommendation by Airbus. When it comes to contaminated runways, there are limitations to crosswind. So, takeoff and landing on dry and wet runways, we use the normal 38 knots recommendation. But for contaminated runways, we use instead this runway assessment matrix provided both in the FCOM as well as in the QRH. And here you will see on the far right side the maximum crosswind limitation. To the left side, you have the runway conditions, which will then be used to match the appropriate level of braking as well as the maximum crosswind. Pilots are trained to use this during the performance course. And now on to the speed limitations on the aircraft, starting with the cockpit windows. Maximum speed for cockpit window operation, means opening and closing the cockpit sliding window, is 200 knots. Not that I recommend opening the cockpit window at 200 knots. Maximum speeds for flaps and slats are also structural limitations, but now placed on the flaps and slat panels. These speeds right here are for the pilots to memorize and know, but they are also placarded inside the cockpit on the instrument panel. The maximum speed in clean configuration is VMO and MMO. We're going to cover that in the next slide. The maximum speed for flaps 1, that means the lever, flaps and slat lever set to position 1 and configuration 1 with only slats out, which is a configuration you will only experience in flight coming in and configuring for an approach, is 230 knots. It is used to slow down the aircraft from green dot speed in order for you to further configure the aircraft. It is also used for holding to get better fuel consumption during holding. Maximum speed for configuration 1 plus F. We still call it configuration 1. The lever is still set to position 1, but as you have learned in the systems presentation, flaps 1 plus F is only attainable when taking off. Maximum speed is 215 knots. Maximum speed with flaps 2 selected and extended is 200 knots. Flaps configuration 3 is 185 knots. And config full is 177 knots. Always make sure you know these values as they are very important to the limitations on the aircraft. Maximum operating speed for the aircraft is VMO or MMO, 350 knots for VMO and Mach 0.82 for MMO. The changeover from VMO to MMO and vice versa is automatic in this aircraft, and it happens at 25,000 feet, as you can see here. Maximum speeds for the landing gear is divided into VLE and VLO. VLE is for landing gear extended. It means the landing gear down and locked and landing gear doors closed on this aircraft. Maximum speed 280 knots. The maximum speed for operating the landing gear with extension, that means putting the landing gear down, is 250 knots. This limitation is placed there to ensure that we don't do damage to the landing gear doors, as they would have to open for the landing gear to extend. VLO for retraction is limited to 220 knots. And this limitation is a lower speed because it places a limitation on the nose wheel, which have to retract forward into the nose of the aircraft, into the airflow. The maximum tire speed, maximum ground speed in this aircraft is 195 knots. Minimum control speeds also exist for this aircraft. However, I have not listed them right here as they are a table in your FCOM, and they are not for pilots to memorize and know. You are, however, required to know exactly where to find the VMC limitations and understand the limitation itself. Why do we have VMC speeds, both for ground, airborne, and landing? All of this we have covered in the performance in ATPL theory, as well as in the basic of aerodynamics. Then we have limitations on taxiing. Maximum taxi speed during turns should not exceed 20 knots if the weight of the aircraft is above 76 tons. That means you're maxed out on weight. And finally, wipers, maximum operating speed is 230 knots. Next up are the limitations on weight and center of gravity. The weight limitations in this aircraft are specific to the aircraft and definitely specific to the A318, 19, 20, and 21. I have listed the major weights here for the A320 aircraft. However, as it mentions right here on all of them, you do have to refer to the appropriate limitation in your FCOM. Maximum taxi weight, also referred to as maximum ramp weight, is 77,400 kilograms in the A320. This is slightly above the maximum takeoff weight, as you can see here, which is 77,000 kilograms. on brake release. This means we must be at 77 tons by the time we apply takeoff power with the intent to take off. So why do we have a slightly higher weight for ramp and taxi than we do for takeoff? Well, this is to ensure that we can carry the maximum amount of payload. We're going to be consuming fuel taxiing out to our takeoff position. And if we were already at maximum takeoff weight on the ramp, we would then be using that weight for fuel which we're going to burn on the ground, which could have been used for payload. Maximum landing weight in the aircraft I have listed here as 66,000 kilograms. I have listed it because at 66 tons, any landing above this is considered an overweight landing procedure. As it notes down here, in exceptional cases, in-flight turnbacks, diversions, immediate return back to the airport after takeoff, an immediate landing at a weight above the maximum landing weight is permitted, provided the pilots follow the overweight landing procedure. This aircraft is not equipped with fuel jettison equipment, fuel dumping capability. Aircraft that can meet the landing requirement structurally at full takeoff weight do not require fuel jettison equipment. So if we have to come back and land immediately after takeoff at our maximum takeoff weight, we can do so knowing the aircraft is structurally strong enough to withstand that landing, provided we follow the overweight landing procedure. Maximum CO fuel weight and minimum weight on the aircraft can be found in the A320 Limitations chapter, and the dry operating mass can be found in the weighing schedule and in your mass and balance documentation for the aircraft. The limitations on center of gravity are placed to ensure both maneuverability and controllability of the aircraft. As we covered in great detail in mass and balance in your ATPL theory, and again during the performance course here in the 320, the CG limits right here must never be exceeded. The CG must be within limits at all times during ground operation, from zero fuel weight all the way up to maximum weight, during taxiing, takeoff, flight, and landing. I have brought forward this CG envelope from the AFCOM, which color codes 3 envelopes on top of each other for maximum zero fuel weight, maximum landing weight, and maximum takeoff weight. You can also see the most forward limit of the center of gravity and the most aft limit over here on the right side for the center of gravity for the individual envelopes. Center of gravity is calculated either using the electronic flight bag or manually on the CG documentation for the aircraft prior to every flight. Always ensure your CG is placed within the envelopes appropriate for the flight phase. Center of gravity limits are given as a percentage Mach because we are flying with an airfoil design which has a swept back wing design. The percentage Mach or percentage of the reference chord length is given aft of the leading edge. The reference chord length is 4.193 meters long, and it's situated, the leading edge Mach starts at 16.31 meters aft of the aircraft's nose. Both of those values are given to be able to calculate manually the position of center of gravity. We covered this in mass and balance in your ATPL theory. The CG must always be within these limits regardless of fuel loading on the aircraft. And that was it on the aircraft general limitations. Let's jump into some of the limitations that are placed on the specific individual systems, starting with the bleed, pressurization, and ventilation system. For the air conditioning system, a general limitation recommendation is that with passengers on board, it is not recommended to exceed 20 minutes without air conditioning supply. The lack of fresh air within the cabin will significantly reduce the cabin air quality. APU bleed with the use of a high pressure air starter unit is prohibited. The flight crew must not use bleed air from APU and from a ground high pressure start unit at the same time. This is to prevent adverse effects to the bleed air system, mainly the bleed air valves. This will cause damage to the valves. For the avionics on the aircraft, we have limitations based on temperatures outside. The avionics ventilation system passes air over the avionics in the avionics bay below the cockpit, as well as pass instruments within the cockpit and circuit breakers. During ground operation and depending on the outside air temperature, the flight crew must limit the time the aircraft has electrical power supply on the normal avionics, and this is limited to temperatures which are above 49 degrees Celsius. Between 49 and 55, it's 2 hours maximum use. 55 to 60 degrees Celsius, 1 hour use. And from 60 degrees to 64 degrees Celsius, which is also the maximum operating temperature for the aircraft outside, that is half an hour. Having hot air like this blowing over the avionics is not going to cool effectively the avionics and could cause damage to all the components within this avionics bay. The cabin pressurization, as we discussed in the presentation on pressurization, has limitations that are very, very important. The cabin operates with a lower altitude than outside. Because of that, pressure exists between the outside and the inside, with a higher pressure inside the cabin than outside when we operate the aircraft in flight. This means that there is a pressure difference between outside and inside known as differential pressure. The maximum positive differential pressure is 9 psi. That's with a higher pressure inside the cabin than outside. The maximum negative differential pressure is 1 psi, and that will be with a higher pressure outside than inside. It's very unlikely to experience maximum negative differential pressure, hence the value is very low compared to that of a positive differential pressure, which we always have when we pressurize a cabin. The safety valve is set to operate at 8.6 psi, meaning if the differential pressure between outside and inside exceeds 8.6 psi, then it operates to let air out of the cabin to maintain the pressure limit at 8.6 psi. Bringing the diagram up a little bit closer, we can also see that this diagram, while having the normal operating range here, with the differential limitations, positive and negative, given, it also gives us crucial altitudes to operating the pressure in the cabin. Normal operating range has a limitation which is minimum cabin altitude selection of minus 2,000 feet. Maximum cabin altitude selection is 14,000 feet. This is the maximum selection we can select on the overhead panel manually for pressurization, and this covers all airports on the planet. But what we have to pay very close attention to here is the maximum normal cabin altitude is 8,000 feet. That means the environment inside the cabin will not, in normal conditions, exceed 8,000 feet of pressure altitude. We may be flying at 39,000 feet, but the inside cabin environment is limited to 8,000 feet. And that's going to cause a pressure difference between outside and inside close to the limit for the aircraft. Cabin altitude warning triggers at 9,550 plus or minus 350 feet. And the outflow valve completely closes at 15,000 feet, trying to prevent air from going out of the cabin to the atmosphere, and this is something that will happen during rapid or explosive decompression. There's also limitation on using low pressure at the same time. The lower pressure comparatively to the bleed comes from the pack and the low pressure air conditioning unit on the ground. Flight crews must not use conditioned air from the packs and the low pressure air conditioning unit at the same time to prevent any adverse effects on the air conditioning system. And that was it on the air bleed condition and pressurization. There are limitations also on autoflight. The autoflight chapter and the autoflight limitations chapter are the biggest chapters in the FCOM. I have picked out the limitations from autoflight that are most specific to your type rating, but you must still ensure you go through every limitation for autoflight to cover all your bases. The minimum use of autopilot for takeoff is 100 feet AGL. But there is an internal logic in the aircraft that limits the use of the autopilot or prohibits it from being turned on until minimum 5 seconds after liftoff. So even if you try to engage it immediately, it would only come on 5 seconds after liftoff. During approach, the minimum use of the autopilot, hence how far can you go down on an approach before you have to disconnect the autopilot, depends on the approach you're flying. For a non-precision approach F glide slope, this is for FMS glide slope approaches, it is 200 feet AGL. For non-precision approaches with final approach vertical speed or FPA use for vertical, it's 250 feet AGL. For circling approaches, it is 500 feet AGL. For ILS, this is ILS Cat 1 shown on the FMA. And in the presentation on autoflight and talking about FMA capability, we talked about the Cat 1, Cat 2, and Cat 3 shown in the approach capability column, fourth column on the FMA. With Cat 1 shown on the FMA, your minimum use of autopilot is 160 feet AGL. You are in Cat 1 intending to land the aircraft manually. And while I do not recommend you fly the aircraft all the way down to 160 feet AGL prior to taking manual control, this is the limitation. Minimum use of autopilot for DLS with no auto land on the FMA is 160 feet AGL. DLS stands for GBAS Landing System. GBAS is ground-based aerial surveillance, and it is a ground-based system using GPS, as you learned in radio navigation, enhancing GPS capabilities and allowing aircraft to land with greater accuracy where GPS signals are verified and integrated into signals coming from the ground. Integrity monitoring is a big part of the GBAS installation. This was covered in great detail in your radio navigation ATPL theory. For ILS Cat 2 or ILS Cat 3 Autoland, we don't have a minimum use of autopilot because we're doing autoland. But ILS Cat 2 with manual landing has a minimum use of autopilot of 80 feet AGL. After manual go around, the limitations for minimum use of autopilot is the same as after takeoff. It's 100 feet AGL. And in all other phases, the minimum use is 500 feet AGL. The flight management function is the third loop and highest loop of automation on this aircraft. We covered this in the APPI briefing. Limitations placed on the use of the flight management function is to laterally and vertically navigate the aircraft using the flight management and guidance system. For use of the FMS landing system, the FLS approach. This is part of the PBN approach capability. RNPAR operation, use of nav mode in normal operation and for IRS navigation performance. Check your FCOM limitations chapter for more detail on the flight management function limitations. The automatic approach capability is also part of the auto flight limitations chapter. When using the automatic approach capability in ILS Cat 2, the minimum decision height is 100 feet AGL, not to be confused with the minimum use of autopilot that we just covered. With an ILS Cat 3, it is divided into fail passive, we call that Cat 3 single, or fail operational, Cat 3 dual. In the chapter on autoflight, I covered the difference between single and dual, being in Cat 3 dual, we have 2 autopilots, 1 active, 1 standby, and the capability allows the autoland, the aircraft, to continue flying if it loses an autopilot, hence why it's called fail operational. If we have ILS Cat 3 capability, well then we have the option of doing the automatic approach to a minimum decision height of 50 feet AGL if you have fail passive, that means Cat 3 single, or fail operational Cat 3 dual takes you down to a minimum decision height of 0, but we instead use and have a minimum alert height, which in this aircraft is 100 feet AGL. A decision height and an alert height are not the same thing. A decision height is set so pilots have to get and establish visual contact with the environment, with the airport runway, approach lighting system, etc., prior to commencing the landing. If you don't have that, by the time you reach decision height, you must initiate a go-around. You are not able to land. With autoland, we have the capability of landing without seeing the runway in front of us. But the capability of the autoland depends on the systems, of course, working. The alert height is the minimum height, which divides the scenario of initiating a go-around, aborting the landing, and continuing the landing even if you have a failure. Above the alert height, any failures triggering the alert height will prompt the pilots to initiate a go-around. Below the alert height, pilots are to disregard any failures other than the ones that are triggered by the auto land warning light. Failures that directly impact the capability of the aircraft to land itself will trigger through this auto land warning light. And if this is the case, the pilots will have to take manual control immediately. But any other failures, the aircraft is capable of continuing and carrying out the auto land. So when pilots come in for an auto land, we are aware of the alert height and we are monitoring very closely the auto land light for warnings at low altitudes. Note that the auto thrust must be on and at least one autopilot must be engaged in approach mode, and Cat 3 single as a minimum must be displayed on the FMA in order for you to use the auto land capability of the aircraft. Cat 3 without decision height, that means with auto land, does not use a decision height. It instead uses a minimum requirement for the runway visual range, that is the horizontal distance visibility, and this is limited to minimum 75 meters. RVRs are reported at airports when low visibility is encountered. Autoflight also has limitations for single engine. Cat 2 and Cat 3 fail passive single. Autoland are only approved in configuration full, and if engine out procedures are completed before reaching 1,000 feet in approach. So you must have dealt with the engine failure prior to 1,000 feet in order for you to commence and continue the approach. Maximum crosswind for auto land and automatic landing limitations. They're given in your limitations chapter in the FCOM. And that was it on the auto flight chapter. Covering the rest of the systems throughout, we'll start with the APU. As we learned in the APU presentation, after 3 consecutive APU start attempts, the electrical starter motor must cool down, and the flight crew must therefore wait minimum 60 minutes prior to 3 new attempts. Maximum end speed for the APU is 107%. Maximum EDT for APU start is 1090 degrees Celsius if the altitude is below 35,000 feet, and if the altitude is above 35,000 feet, you're limited to 1120 degrees Celsius. Maximum EDT for APU running is 675 degrees Celsius. For the APU limitations, we also covered this diagram in detail in the presentation. This showed us the APU ground operation right here, where we can operate the APU on the ground up to 14,500 feet. So no limitation there, and down to minus 2,000 feet. But where we had to pay specific attention was the yellow marking right here, which states that the use of the APU bleed together with electrical output is limited to 22,500 feet. And above 22,500 feet, the APU is only capable of providing electrical output. This was a limitation that was placed because of the lack of density pressure at higher altitude. The APU is simply not capable of drawing in the air to compress to also bring out bleed air while running the load compressor and the shaft for use on the other components such as the electrical generator. The other limitation that I was very carefully explaining in the APU limitations chapter was the APU battery restart limit. This limit, as you can see, is 25,000 feet, but it only exists if you're attempting to start the APU on batteries only. That means emergency electrical configuration. If you're attempting to start the APU in flight from the normal electrical supply, well then the normal operating restart limit here is not a limiting factor, as it sits at 41,000 feet. And our maximum operating altitude was 39,000 feet and 800. APU bleed can be used to assist in engine starting in flight up to a maximum altitude of 20,000 feet. The maximum altitude for the APU to supply air conditioning and pressurization for a single pack is 22,500 feet. But if the APU is to supply air conditioning and pressurization for both the packs as a single bleed source, well then you're limited to 15,000 feet. The use of APU bleed for wing anti-icing is not permitted. There are also a few limitations for the cabin. Power supply for portable electronic devices, that means the in-seat power supply in the cabin. This has a limitation not to be operated and on during takeoff and landing. Use of mobile phones and mobile devices with DSM capability, as well as in-flight Wi-Fi, etc., is also limited. The use of mobile phones is prohibited in the toilets and in the cockpit, and it is prohibited to use DSM onboard systems below 3,000 meters, that means approximately 10,000 feet, and in some geographical areas. The engines, although specific to the aircraft you're flying, does have limitations to them. I only brought up the limitations here that are universal for all the engines. Toga power is limited to 5 minutes with 2 engines running. and 10 minutes with single engine operation. In an emergency, we can use toga power as long as the emergency situation calls for it. But these limitations on EDT are placed there for a reason, so as to not overheat the engine. EDT limits for the use of toga power, together with maximum EDT for starting the engines, these will be covered by you in the FCOM limitation chapter. Maximum N1 and N2 speeds, as well as oil limitations for temperature, pressure, and quantity can all be found in your appropriate FCOM limitation chapter. For the engines, there are limitations to the air starter motor, not as strict as the one on the electrical starter motor for the APU, but this is still a limitation that needs to be obeyed if you have to perform, for example, a manual engine start. A standard automatic start that includes up to 3 start attempts by the FEDEC is considered 1 cycle. For ground starts, automatic or manual, a 20-second or in some cases 60-second pause is required between successful cycles. A 15-minute cooling period is required subsequent to 3 failed cycles. Remember, each cycle includes 3 attempts. The starter must not be engaged when N2 is above, and that is for your individual airplane engine. The limitations on reverse thrust are universal. Selection of reverse thrust is prohibited in flight. It's also protected against such selection. Backing up the aircraft with reverse thrust is not permitted. A maximum reverse thrust should be cancelled or not used below 70 knots, although idle reverse can be used down to the aircraft stops. This limitation on max reverse is placed to minimize the risk of foreign objects going into the engine through the intake at low forward speeds. In the performance presentation, we talked about the use of flexible temperature for takeoff. This was a way to optimize the takeoff and minimize the wear and tear on the engine, prolonging the engine's life. Flexible takeoff, that means takeoff on reduced thrust, is permitted only if the airplane meets all the performance requirements at the takeoff weight with the operating engines at the thrust available with the flexible temperature set, T-flex. We calculate this when we put the values for the current conditions into the EFB, or when we manually calculate it from the FCOM takeoff tables to ensure we do meet that requirement. Takeoff at a reduced thrust is permitted with any inoperative item affecting performance only if the associated performance shortfall has been applied to meet the above requirements. It means you have used the appropriate tables to account for said failures. All of this is covered in the performance course. Flex takeoff is never permitted on contaminated runways. T-flex, that means the temperature value for flex, cannot be higher than the T-flex max, lower than the outside air temperature, or lower than the flat rated temperature T-ref for the engine. Another way of saving performance for takeoff, if you don't need full power for takeoff, is doing what's called a derated takeoff. Does not optimize the same way that flexible temperature takeoffs do, but it is still better than performing a toga power takeoff. Selection of toga thrust is not permitted when a derated takeoff is performed, except when requested by an abnormal emergency procedure. The use of reduced thrust takeoff, flex takeoff, is not permitted in association with a derated takeoff. And the use of derated takeoff is permitted regardless of the runway conditions. That means we can use a derated takeoff for contaminated runways, something that's not possible with a flexible temperature. Crosswind operations on the ground for engines while limitations on engines for start and takeoff is specific to your engine, so make sure you cover that in your FCOM. For flight controls, there were a few limitations. First and foremost, maximum altitude for flaps and slats extended is 20,000 feet. And then use of flight controls, rapid and large alternating control inputs, especially in combination with large changes in pitch, roll, and yaw, large side slip, etc., may result in structural failure at any speed. So do not attempt to fly this aircraft like a fighter aircraft. It isn't built for it. Fuel systems also had limitations. This was based on the fuel we're using. Although it states in the FCOM and in the limitations chapter that the engines are capable of using more than a dozen different types of fuels, there are really only two fuels you will get your hands on for commercial use: Jet A1 and Jet A. Jet A1 has a minimum temperature of minus 43 and a maximum temperature of 55 degrees Celsius, whereas Jet A has a slightly lower value of minus 36 degrees to positive 55 degrees Celsius. The various types of fuel can be mixed in any proportions. However, the lower, most restrictive value up here will then apply. Maximum allowable fuel imbalance depends on the fuel system configuration, the use of auxiliary tanks, the use of and capability of the wing tanks, outer and inner. Therefore, the imbalance should be checked with the appropriate manual for the aircraft you fly. Refer to your FCOM. Minimum fuel quantity for all aircraft is 1,500 kilograms, and no takeoff is allowed if fuel wing tank low level is displayed on the engine warning display on the ECAM. For ice and rain protection, we talked about definitions rather than limitations. So I want to run through the same here. Definition of icing conditions in the aircraft. In flight, if the outside air temperature is below 10 degrees and you have visible moisture in any form, such as clouds, fog, 1 statute mile visibility, or rain, snow, sleet, crystals, etc., then you have icing conditions. Or on the ground, and for takeoff, if the outside air temperature is below 10 degrees and you're operating on ramps or taxiways or runways where the surface has snow, standing water, or slush that may be ingested into the engines or freeze the engines, nacelles, or probe sensors, then you have icing conditions. Definition of ice buildup, of ice accretion. You have ice accretion, and it is considered severe if the ice accumulated on the airframe reaches approximately 5 millimeters in thickness. And definition of frost, hoarfrost, on the upper surface of the aircraft, specifically something you experience during cold, calm nights where the temperature dropped below the dew point with freezing surfaces and a lot of moisture in the air. You will find a white crystalline deposit which usually develop uniformly on exposed surfaces in cold and cloudless nights, and that's the upper surface of an aircraft. It is so thin that you're actually able to see the features and markings on the airplane underneath it. But make no mistake, hoarfrost is still devastating when it comes to lift and the capability of an airfoil to generate lift. Do not ever attempt to take off with the aircraft covered with frost. Maximum speed for the window wipers we've already covered. That was 230 knots. The landing gear also has limitations, although we have covered some of them already. Here's one we haven't covered. The braking system, first and foremost, is not designed to hold the aircraft in a stationary position with high thrust applied to at least one engine. Maximum brake temperature for takeoff is 300 degrees Celsius, brake fans off, and 150 degrees Celsius with the fans on. Maximum speeds for the landing gear: VLE, landing gear extended, was 280 knots. VLO for extension was 250. VLO for retraction was 220. And maximum tire speed was 195. The nose wheel steering has a maximum steering angle of plus or minus 85 degrees on either side. This, of course, is a limitation that will not be applicable if the aircraft is being towed on the ground. Taxi with deflated or damaged tires also requires the careful operation from the crew. Maximum speed with deflated or damaged tire: one tire deflated per gear, it's 7 knots. 2 tires deflated on the same gear, 3 knots. And then the maximum nose wheel steering is limited to plus or minus 30 degrees with deflated or damaged tires. For the navigation system, we had limitations based on the IRS and the capability of the aircraft to use IRS specifically at high latitudes. Ground alignment of the IRS is possible in latitudes between 82 degrees north and 82 degrees south. Above these latitudes, the IRS alignment is not properly accurate. In nav mode, the IR will not provide valid magnetic heading and track north of 70 degrees north, between 90 degrees west and 120 degrees west, north of 82 degrees north, and south of 60 degrees south. Flying at latitudes beyond these is prohibited with the use of the IRS for navigation. And that brings us to the oxygen system. The minimum pressure for cockpit oxygen systems, which is something that's checked by the crew during the cockpit preparation, can be found in the FCOM limitations chapter. This table I have not put up here, but it uses minimum pressure to ensure the oxygen that is in the system is sufficient to meet the requirements for the occupants in the cockpit based on the outside air temperature. We cover this in more detail in the oxygen presentation in this A320 ground school. The ground proximity warning system, which we covered in the surveillance part of the A320 ground school, had limitations on the use of the predictive GPS function. That means when you're using terrain featured databases. The aircraft navigation must not be based on the use of the terrain display. The terrain display is intended to serve as a situation awareness tool only and may not provide the accuracy on which solely based terrain avoidance maneuvering. The EGPWS, the Enhanced Ground Proximity Warning System, the predictive function, should be inhibited. That means terrain off on the overhead panel. When the aircraft position is less than 15 nautical miles from an airfield for which operation to and from is not incorporated into the predictive GPWS database, for specific approach or departure procedures which have previously been identified as potentially causing or expected spurious terrain alerts. Only aircraft with the man-made obstacle function, which is an additional function for the GPWS, can display obstacles on the ND and trigger alerts based on dedicated database, which includes artificial obstacles worldwide. That was it on the presentation on limitations. I hope this helped to clarify the limitations on this aircraft. Remember, limitations, memory items, they are the essential backbone of your type rating. Always know your limitations.